In 1807, Joseph Fourier made a claim that scandalized the French Academy. Any function, no matter how irregular, can be written as a sum of sine and cosine waves. Lagrange objected. Laplace was skeptical. The claim turned out to be essentially correct. And the mathematics that grew from it now runs through nearly every system that processes signals, images, or language. Imagine you smell a complex aroma, a single tangled thing. A trained chef decomposes it: basil, garlic, tomato. The Fourier transform does this to signals. It takes them apart, not into moments, but into frequencies. 3 simple waves, each a pure frequency. Their sum, complex but entirely determined by 3 frequencies and 3 amplitudes. How does the transform detect which frequencies are present? Take your signal, multiply it by a test wave, and measure the total area under the product. When the test frequency matches, peaks align, the product stays positive and the area grows. When it doesn't match, positive and negative areas cancel. Large area means present. 0 area means absent. That is the whole mechanism. There is a second way to see the same computation. Instead of multiplying and measuring area, imagine winding the signal around a circle. If the winding speed matches a frequency in the signal, the peaks always land on the same side. The center of mass shifts. If it doesn't match, the peaks scatter. The center of mass stays at the origin. Both representations contain exactly the same information. The Fourier transform is a lossless, reversible change of perspective. What you hear, a tangled waveform. What it is made of, 3 clean spikes. The power of having 2 representations is operational. You have a recording with a high-pitched whine. In the time domain, the whine is tangled into every sample. But in the frequency domain, the whine is a single spike, sitting apart. Zero it out, transform back, and the whine is gone. The original transformer needed a way to tell the model where each token sits in a sequence. The solution was sinusoidal positional encodings. Each dimension encodes position at a different frequency. This is a Fourier basis. The transformer receives position pre-encoded in the same mathematical language that signal processing has used for 2 centuries. When Gaussian noise is added to an image, it contributes energy uniformly across all frequencies. High-frequency details, edges, textures are buried first. The denoising network must learn to separate structured frequency components from the noise floor. Audio is where Fourier analysis began. Speech is inherently spectral. Pitch, timbre, vowel identity are all frequency domain quantities. When Noument speaks, the text becomes a Mel spectrogram before it ever becomes sound. When an agent listens, Whisper's first operation is a forward Fourier transform. The Fourier transform is active infrastructure in our multi-agent system. 5 capabilities: speaking, listening, gesturing, imaging, thinking. 5 Fourier dependencies. The transform is not something we chose to use. It is embedded in the providers and architectures that our system dispatches to. It was there before we built Nouments, and it would remain if we replaced every component. Fourier analysis is not a technique that AI borrowed. It is a mathematical structure that keeps appearing because the problems demand it. The Fourier basis is canonical. It diagonalizes convolution, preserves energy, treats all frequencies equally, and has an efficient algorithm. When a problem involves signals, periodicity, or positional structure. The Fourier basis is not one option among many. It is the mathematically natural choice. Fourier did not know about transformers or diffusion models. He was studying heat conduction in metal plates. But the mathematics he developed to describe how heat flows through matter turned out to describe how information flows through neural networks. The same equations, the same decomposition, the same insight. Complex structure is simple structure superimposed.